Okay, back with structure and interpretation of computer programs, section 3.3.3 representing tables. When we studied various ways of representing sets in chapter 2, we mentioned in section 2.3.3 the task of maintaining a table of records indexed by identifying keys. In the implementation of data-directed programming in section 2.4.3, we made extensive use of two-dimensional tables in which information is stored and retrieved using two keys. Here we see how to build tables as mutable list structures. And here in figure 3.22 we see a table represented as a headed list. Okay, we first consider a one-dimensional table in which each value is stored under a single key. We implement the table as a list of records, each of which is implemented as a pair consisting of a key and the associated value. The records are glued together to form a list by pairs whose cars point to successive records. These gluing pairs are called the backbone of the table. In order to have a place that we can change when we add a new record to the table, we build the table as a headed list. A headed list has a special backbone pair at the beginning, which holds a dummy record, in this case the arbitrarily chosen symbol table, and figure 3.22 shows the box and pointer diagram for the table ABC with associated values 1 to 3. Let's see. Okay, so we have this sort of, this is the backbone, right? In the backbone the car is pointing to a pair holding the key and the key in the car and the value in the coder, and the coder points to the other pair in the backbone. Okay, I got it. To extract information from a table, we use the lookup procedure, which takes a key as argument and returns the associated value, or false if there is no value stored under that key. Lookup is defined in terms of the ASOC operation, which expects a key and a list of records as arguments. Note that ASOC never sees the dummy record. ASOC returns the record that has the given key as its car. Okay. Lookup then checks to see that the resulting record returned by ASOC is not false, and returns the value, the coder of the record. Okay, I got this. To insert a value in a table under a specified key, we first use ASOC to see if there is already a record in the table with this key. If not, we form a new record by consing the key with the value and inserting these at the head of the table's list of records after the dummy record. If there already is a record with this key, we set the coder of this record to the designated new value. The header of the table provides us with a fixed location to modify in order to insert the new record. Okay. To construct a new table, we simply create a list containing the symbol table. Okay. Two-dimensional tables. In a two-dimensional table, each value is indexed by two keys. We can construct such a table as one-dimensional table in which each key identifies a subtable. Figure 3.23 shows the box and pointer diagram for the table with math and letters. which has two subtables. The subtables don't need a special header symbol since the key that identifies the subtable serves this purpose. When we look up an item, we use the first key to identify the correct subtable. Then we use the second key to identify the record within the subtable. Yeah, this is pretty straightforward, I would say. Not too much clear why this is not immediately pointing um, is not immediately pointing to this one. Probably because it gives you space to add a new subtable. Probably the reason is this. Okay, let's see if the book says something. To insert a new item under a pair of keys, we use ASOC to see if there is a subtable stored under the first key. If not, we build a new subtable containing the first record and insert it under the table under the first key. Yeah. If a subtable already exists for the first key, we insert a new record into this subtable, using the insertion method for one-dimensional tables described above. Creating local tables. The lookup and insert operations defined above take the table as an argument. This enables us to use programs that access more than one table. Another way to deal with multiple tables is to have separate lookup and insert procedures for each table. We can do this by representing a table procedurally as an object that maintains an internal table as part of its local state. When sent an appropriate message, this table object supplies the procedure with which to operate on the internal table. Here is a generator for two-dimensional tables represented in this fashion. Okay. Using MakeTable, we could implement the get and put operations used in section 2.4.3 for data-directed programming as follows. Okay, get takes as arguments two keys and put takes as argument two keys and a value. Both operations access the same local table, which is encapsulated within the object created by the call to make table. Okay, then we have a bunch of exercises. Section 3.3.4, a simulator for digital circuits. Let me see the index. Okay, chapter 3. Okay, we have a simulator for digital circuits and then propagation of constraints. Okay. Designing a simulator for digital circuits. Designing complex digital systems, such as computers, is an important engineering activity. Digital systems are constructed by interconnecting simple elements. Although the behavior of these individual elements is simple, networks of them can have very complex behavior. Computer simulation of proposed circuit designs is an important tool used by digital systems engineers. In this section, we design a system for performing digital logic simulations. This system typifies a kind of program called an event-driven simulation, in which actions, events, trigger further events that happen at a later time, which in turn trigger more events, and so on. Our computational model of a circuit will be composed of objects that correspond to the elementary components from which the circuit is constructed. And in figure 3.3 3.24, we see primitive functions in the digital logic simulator. We see the inverter, the AND gate, and the OR gate. There are wires which carry digital signals. A digital signal may at any moment have only one of two possible values, 0 and 1. There are also various types of digital function boxes which connect wires carrying input signals to other output wires. Such boxes produce output signals computed from their input signals. The output signal is delayed by a time that depends on the type of the function box. For example, an inverter is a primitive function box that inverts its input. If the input signal to an inverter changes to 0, then one inverter delay later, the inverter will change its output signal to 1. If the input signal to an inverter changes to 1, then one inverter delay later, the inverter will change its output signal to 0. We draw an inverter symbolically as in figure 3.24, and an AND gate, also shown in figure 3.24, is a primitive function box with two inputs and one output. It drives its output signal to a value that is the logical end of the inputs. That is, if both of its input signals become 1, then one AND gate delay time later, and the AND gate will force its input signal to be 1. Otherwise, the output will be 0. An OR gate is a similar two-input primitive function box that drives its output signal to a value that is the logical OR of the inputs. That is, the output will become 1 if at least one of the input signals is 1. Otherwise, the output will become 0. Okay, this is standard. We can connect primitive functions together to construct more complex functions. To accomplish this, we wire the outputs of some function boxes to the inputs of other function boxes. For example, the half adder, shown in figure 3.25. So here we see the inverter, we see the AND gate, we see the OR gate. Yeah, consists of an OR gate, two AND gates, these two, and an inverter. It takes two input signals, A and B, and has two output signals, S and C. S will become 1 whenever precisely one of A and B is 1, and C will become 1 whenever A and B are both 1. We can see from the figure that because of the delays involved, the outputs may be generated at different times. Many of the difficulties in the design of digital circuits arise from this fact. We will now build a program for modeling the digital logic circuits we wish to study. The program will construct computational objects modeling the wires which hold the signals. Function boxes will be modeled by procedures that enforce the correct relationships among the signals. One basic element of our simulation will be a procedure make wire, which constructs wires. For example, we can construct 6 wires as follows. Okay. We attach a function box to a set of wires by calling a procedure that constructs that kind of box. The arguments to the constructor procedure are the wires to be attached to the box. For example, given that we can construct AND gates, OR gates, and inverters, we can wire together the half adder shown in figure 3.25 like this. Okay, OR gate, we have input signals A, B, D, A, B, C. The inverter takes only one input and one output, and the AND gate instead takes 2 inputs and 1 output. Okay. Better yet, we can explicitly name this operation by defining a procedure half adder that constructs this circuit, given the 4 external wires to be attached to the half adder. Okay, we have these external D and E are defined locally and are used inside the circuit, so that we have to pass only the external wires, the two inputs A and B and the two outputs S and C. The advantage of making this definition is that we can use half adder itself as a building block in creating more complex circuits. Figure 3.26, for example, shows a full adder composed of two half adders and an OR gate. We can construct a full adder as follows. Yeah, full adder is a basic circuit element used in adding two binary numbers. Okay. Okay. Okay, now we have three inputs and two outputs. Having defined full adder as a procedure, we can now use it as a building block for creating still more complex circuits. In essence, our simulator provides us with the tools to construct a language of circuits. If we adopt the general perspective on languages with which we approached the study of Lisp in section 1.1, we can say that the primitive function boxes form the primitive elements of the language. That wiring boxes together provides a means of combination, and that specifying wiring patterns as procedures serves as means of abstraction. Primitive function boxes. The primitive function boxes implement the forces by which a change in the signal on one wire influences the signal on other wires. To build function boxes, we use the following operations on wires. So we have get signal, set signal, add action. In addition, we will make use of a procedure after delay that takes a time delay and a procedure to be run and executes the given procedure after the given delay. Using these procedures, we can define the primitive digital logic functions. To connect an input to an output through an inverter, we use add action to associate with the input wire procedure that will be run whenever the signal on the input wire changes value. The procedure computes the logical knot of the input signal and then, after one inverter delay, sets the output signal to be this new value. Okay. An AND gate is a little more complex. The action procedure must be run if either of the inputs to the gate changes. It computes the logical AND using a procedure analogous to logical NOT of the values of the signals on the input wires and sets up a change to the new value to occur on the output wire after one AND gate delay. Okay, a couple of exercises. Representing wires. A wire in our simulation will be a computational object with two local state variables, a signal value, initially taken to be 0, and a collection of action procedures to be run when the signal changes value. We implement the wire using message passing style as a collection of local procedures together with a dispatch procedure that selects the appropriate local operation, just as we did with the simple bank account object in section 3.1.1. Okay, I don't skip this code because I understood what it's doing. The local procedure set my signal tests whether the new signal value changes the signal on the wire. If so, it runs each of the action procedures using the following procedure called each, which calls each of the items in a list of no argument procedures. The local procedure accept action procedure adds the given procedure to the list of procedures to be run, and then runs the new procedure once. With the local dispatch procedure set up as specified, we can provide the following procedures to access the local operations on wires. Wires which have time-varying signals and may be incrementally attached to devices are typical of mutable objects. We have modeled them as procedures with local state variables that are modified by assignment. When a new wire is created, a new set of state variables is allocated by the let expression in makeWire, and a new dispatch procedure is constructed and returned, capturing the environment with the new state variables. The wires are shared among the various devices that have been connected to them. Thus, a change made by an interaction with one device will affect all the other devices attached to the wire. The wire communicates the change to its neighbors by calling the action procedures provided to it when the connections were established. Okay, let me see. Okay, I'll continue till section 3.3.5, and next time we'll see the propagation of constraints. The agenda. The only thing needed to complete the simulator is after delay. The idea here is that we maintain a data structure, called an agenda, that contains a schedule of things to do. The following operations are defined for agendas. Make agenda, empty agenda, first agenda item, remove first agenda item, add to agenda, and current time. Okay. The particular agenda that we use is denoted by the agenda. The procedure after delay adds new elements to the agenda. The simulation is driven by the procedure propagate, which operates on the agenda, executing each procedure on the agenda in sequence. In general, as the simulation runs, new items will be added to the agenda, and propagate will continue the simulation as long as there are items on the agenda. So the following procedure, which places a probe on a wire, shows the simulator in action. The probe tells the wire that whenever its signal changes value, it should print the new signal value, together with the current time and the name that identifies the wire. Okay. We begin by initializing the agenda and specifying delays for the primitive function boxes. Okay, now we define 4 wires, placing probes on 2 of them. Okay. Okay, probe on the outputs, essentially, the sum and the carry. Next, we connect the wires in a half-adder circuit. Set the signal on input to 1 to 1 and run the simulation. Propagate. Okay. The sum signal changes to 1 at time 8. We are now 8 time units from the beginning of the simulation. At this point, we can set the signal on input 2 to 1 and allow the values to propagate. The carry changes to 1 at time 11, and the sum changes to 0 at time 16. Implementing the agenda. Finally, we give details of the agenda data structure, which holds the procedures that are scheduled for future execution. The agenda is made up of time segments. Each time segment is a pair consisting of a number, the time, and a queue. Okay. That holds the procedures that are scheduled to be run during that time segment. We will operate on the time segment queues using the queue operations described in section 3.3.2. The agenda itself is a one-dimensional table of time segments. It differs from the tables described in section 3.3.3 in that the segments will be sorted in order of increasing time. In addition, we store the current time, so that the time of the last action that was processed, at the head of the agenda. The newly constructed agenda has no time segments and has a current time of 0. Okay, an agenda is empty if it has no time segments, clear. To add an action to an agenda, we first check if the agenda is empty. If so, we create a time segment for the action and install these in the agenda. Otherwise, we can scan the agenda, examining the time of each segment. If we find the segment for our appointed time, we add the action to the associated queue. If we reach a time later than the one to which we are appointed, we insert a new time segment into the agenda just before it. If we reach the end of the agenda, we must create a new time segment at the end. The procedure that removes the first item from the agenda deletes the item at the front of the queue in the first time segment. If this deletion makes the time segment empty, we remove it from the list of segments. The first agenda item is found at the head of the queue in the first time segment. Whenever we extract an item, we also update the current time. Okay, a couple of exercises, and here we are, propagation of constraints. Okay, we'll see these in the next video. I'll stop here. See you in the next one. Ciao, ciao.